The chemical substance hydrochloric acid is the aqueous but water-based solution of hydrogen chloride gas. It is a strong acid facilitating wide use. As a highly corrosive liquid, hydrochloric acid should be handled only with appropriate safety precautions. Hydrochloric acid, or muriatic acid by its historical but still occasionally used name, has been an important and frequently used chemical from early history and was discovered by the Islamic alchemist Jabir around the year 800. It was used throughout the Middle Ages by alchemists in the quest for the philosopher's stone, and later by several European scientists, including Glauber, Priestley, and Davy, helping establish modern chemical knowledge. During the Industrial Revolution, it became an important industrial chemical for many applications. Applications include large-scale production of organic compounds such as vinyl chloride for PVC, and MDI and TDI for PUR, and small-scale applications such as the production of gelatin and other ingredients in food and leather processing. Currently, production is approximately 20 million metric tons annually of hydrogen chloride gas. History. Hydrochloric acid was first discovered around the year 800 by Islamic alchemist Jabir by mixing common salt with vitriol, that's sulfuric acid. Jabir discovered or invented many important chemicals and wrote his findings in over 20 books, which carried his chemical knowledge of hydrochloric acid and other basic chemicals for hundreds of years. Jabir's invention of the gold-dissolving aqueous regia, consisting of hydrochloric acid and nitric acid, contributed to the efforts of alchemists trying to find the philosopher's stone. In the Middle Ages, hydrochloric acid was known to European alchemists as spirit of salt or acidium salus. Gaseous hydrogen chloride was called marine acid air. The old pre-systematic name, muriatic acid, has the same origin, muriatic meaning pertaining to brine or salt, and this name is still sometimes used. Notable production was recorded by Basilius Valentinus, the alchemist abbot of the Augustinians Abbey in Erfurt, Germany, in the 15th century. In the 17th century, Johann Rudolf Glauber from Karlstadt, Germany, used sodium chloride salt and sulfuric acid for the preparation of sodium sulfate, releasing hydrogen chloride gas. Joseph Priestley from Leeds, England, prepared pure hydrogen chloride in 1772, and in 1818 Humphrey Davy from Penzance, England, proved that the chemical composition included hydrogen and chlorine. During the Industrial Revolution in Europe, demand for alkaline substances such as soda ash increased, and the new industrial soda process by Nicolas Leblanc enabled cheap large-scale production. In the Leblanc process, salt is converted to soda ash using sulfuric acid, limestone, and coal, releasing hydrogen chloride as a byproduct. Until the Alkali Act of 1863 prohibited it, excess hydrogen chloride was vented to the air. After the passage of the Act, soda ash producers were obliged to absorb the waste gas in water, producing hydrochloric acid on an industrial scale. When early in the 20th century the Leblanc process was effectively replaced by the Solvay process without hydrochloric acid byproduct, hydrochloric acid was already fully settled as an important chemical in numerous applications. The commercial interest initiated other production methods which are still used today, as described below. Today, most hydrochloric acid is made by absorbing hydrogen chloride from industrial organic compounds production. Chemistry. Hydrogen chloride, whose symbol is HCl, is a monoprotic acid which can dissociate, i.e. ionize, only giving up one positive hydrogen ion or a single proton. In aqueous hydrochloric acid, the proton joins a water molecule to form a hydronium ion. The other ion formed is a negative chloride ion. Hydrochloric acid can therefore be used to prepare salts called chlorides, such as sodium chloride. Hydrochloric acid is considered a strong acid since it is practically fully dissociated in water. Monoprotic acids have one acid dissociation constant, Ka, which indicates the level of dissociation in water. For a strong acid like hydrogen chloride, the constant is large. Theoretical attempts to assign a constant to hydrogen chloride have been made. When chloride salts, such as sodium chloride, are added to aqueous hydrogen chloride, they have practically no effect on pH, indicating that the chloride ion is an exceedingly weak conjugate base, and that hydrogen chloride is fully dissociated in aqueous solution. For intermediate to strong solutions of hydrochloric acid, the assumption that the proton molarity, a unit of concentration, equals hydrogen chloride molarity is excellent, agreeing to 4 significant digits. Of the 7 common strong acids in chemistry, all of which are inorganic, hydrochloric acid is the monoprotic acid least likely to undergo an interfering oxidation-reduction reaction. It is one of the least hazardous strong acids to handle. Despite its acidity, it produces the less reactive and non-toxic chloride ion. Intermediate strength hydrochloric acid solutions are quite stable, maintaining their concentrations over time. These attributes, plus the fact that it is available as a pure reagent, means that hydrochloric acid makes an excellent acidifying reagent and acid titrant for determining the amount of an unknown quantity of base in a titration. Strong acid titrants are useful because they give more distinct endpoints in a titration, making the titration more precise. Hydrochloric acid is frequently used in chemical analysis and to digest samples for analysis. Concentrated hydrochloric acid will dissolve some metals to form oxidized metal chlorides and hydrogen gas. It will produce metal chlorides from basic metal compounds such as calcium carbonate or copper 2 oxide. It is also used as a simple acid catalyst for some chemical reactions. Physical properties. The physical properties of hydrochloric acid, such as boiling and melting points, density and pH, depend on the concentration or molarity of hydrogen chloride in the acid solution. They can range from those of water at 0% hydrogen chloride to values for fuming hydrochloric acid at over 40% hydrogen chloride. Hydrochloric acid, as the binary mixture of hydrogen chloride and water, has a constant boiling azeotrope at 20.2% hydrogen chloride and 108.6 degrees Celsius, or 227 degrees Fahrenheit. There are 4 constant crystallization eutectic points for hydrochloric acid, between the crystal form at 68% hydrogen chloride, 51%, 41%, and 25%, and of course ice at 0% hydrogen chloride. There is also a metastable eutectic at 24.8%. Production. Direct synthesis. The large-scale production of hydrochloric acid is always integrated in other industrial-scale chemical industry. In the chlor-alkali industry, salt solution is electrolyzed, producing chlorine, caustic soda, and hydrogen. The pure chlorine gas can be recombined with the hydrogen gas, forming chemically pure hydrogen chloride gas. As the reaction is exothermic, the installation is called a hydrogen chloride oven. The resulting pure hydrogen chloride gas is absorbed in demineralized water, resulting in chemically pure hydrochloric acid. Organic synthesis. The largest production of hydrochloric acid is integrated with the formation of chlorinated and fluorinated organic compounds such as Teflon, Freon, and other CFCs, chloroacetic acid, and PVC. Often, this production of hydrochloric acid is integrated with captive use of it on site. In the chemical reactions, hydrogen atoms are replaced by chlorine atoms, whereupon the released hydrogen atom recombines with the spare atom from the chlorine molecule, forming hydrogen chloride. Chlorination is a subsequent chlorine replacement reaction, producing again hydrogen chloride. The resulting hydrogen chloride gas is either reused directly or absorbed in water, resulting in hydrochloric acid of technical or industrial grade. Industrial market. Hydrochloric acid is produced in solutions of up to concentrated grade at 38% hydrogen chloride. Higher concentrations, up to just over 40%, are chemically possible, but the evaporation rate is so high that storage and handling need extra precautions, such as pressure and low temperature. Bulk industrial grade is level 30 to 34%, optimized for effective transport and limited product loss by hydrogen chloride vapors. Solutions for household purposes, mostly cleaning, are typically 10 to 12%, with strong recommendations to dilute before use. Major producers worldwide include Dow Chemical at 2 million metric tons annually, calculated as hydrogen chloride gas, and FMC, Georgia Gulf Corporation, Tosa Corporation, AkzoNobel, and Tessenderlo at 0.5 to 1.5 metric tons per year each. Total world production for comparison purposes expressed as hydrogen chloride is estimated at 20 metric tons per year, with 3 metric tons per year from direct synthesis and the result as secondary product from organic or similar synthesis. By far most of all hydrochloric acid is consumed captively by the producer. The open world market size is estimated at 5 metric tons per year. Applications. Hydrochloric acid is a strong inorganic acid that is used in many industrial processes. The application often determines the required product quality. Regeneration of ion exchangers. An important application of high-quality hydrochloric acid is the regeneration of ion exchange resins. Cation exchange is used widely to remove ions such as positive sodium and double positive calcium from aqueous solutions, producing demineralized water. Ion exchangers and demineralized water are used in all chemical industries, drinking water production, and many food industries. pH control and neutralization. A very common application of hydrochloric acid is to regulate the basicity, the pH, of solutions. In industry demanding purity, such as the food, pharmaceutical and drinking water industries, high-quality hydrochloric acid is used to control the pH of processed water streams. In less demanding industry, technical quality hydrochloric acid suffices for neutralizing waste streams. Pickling of steel. Pickling is an essential step in metal surface treatment to remove rust or iron oxide scale from iron or steel before subsequent processing, such as extrusion, rolling, galvanizing, and other techniques. Technical quality hydrochloric acid, or the alternative sulfuric acid, is used in steel processing industries. The spent acid has long been reused as ferrous chloride solutions, but high heavy metal levels in the pickling liquor has decreased this practice. Production of inorganic compounds. Numerous products can be produced with hydrochloric acid in normal acid-base reactions, resulting in inorganic compounds. These include water treatment chemicals such as iron-free chloride and polyaluminium chloride. Both iron-free chloride and PAC are used as flocculation and coagulation agents in wastewater treatment, drinking water production, and paper production. Other inorganic compounds produced with hydrochloric acid include road application salt, calcium chloride, nickel-2 chloride for electroplating, and zinc chloride for the galvanizing industry and battery production. Production of inorganic compounds. The largest hydrochloric acid consumption is in the production of organic compounds, such as vinyl chloride for PVC, and MDI and TDI for polyurethane. This is often captive use, consuming locally produced hydrochloric acid that never actually reaches the open market. Other organic compounds produced with hydrochloric acid include bisphenol A for polycarbonate, activated carbon and ascorbic acid, as well as numerous pharmaceutical products. Other applications. Hydrochloric acid is a fundamental chemical, and as such it is used for a large number of small-scale applications such as leather processing, household cleaning, and building construction. In addition, a way of stimulating oil production is by injecting hydrochloric acid into the rock formation of an oil well, dissolving a portion of the rock and creating a large pore structure. Oil well acidizing is a common process in the North Sea oil production industry. Many chemical reactions involving hydrochloric acid are applied in the production of food, food ingredients, and food additives. Typical products include aspartame, fructose, citric acid, lysine, hydrolyzed protein, and gelatin. Food grade, extra pure hydrochloric acid can be applied when needed for the final product. Hydrochloric acid and living organisms. In physiology, gastric acid, the human digestive fluid, consists mostly of hydrochloric acid. This acid is secreted by parietal cells in the stomach epithelium. Parietal cells contain an extensive secretory network called canaliculi, from which the hydrogen chloride is secreted into the stomach. The resulting highly acidic environment causes proteins from food to unfold or denature, and this exposes the protein's peptide bonds. Enzymes such as pepsin and trypsin help digestion by breaking the bonds linking amino acids, a process known as proteolysis. In addition, many bacteria cannot survive in such an acidic environment, preventing the body from becoming infected by bacteria found in foods. Overacidity in the stomach can lead to heartburn or peptic ulcers. Drugs called proton pump inhibitors prevent the body from making excess acid in the stomach, while antacids neutralize existing acids. Achlorohydria is the inability of parietal cells to produce the required amount of hydrochloric acid in the stomach, potentially leading to gastroenteritis. In the life cycle of living bone material, specialized bone reabsorbing cells, called osteoclasts, also produce hydrochloric acid to dissolve bone. Hydrogen ions react with carbonated hydroxyapatite, the main mineral in bone, and break it down into calcium ions, phosphoric acid, carbonic acid, and water. Chemical weapons. Phosgen, carbon chlorate, was a common chemical warfare agent used in World War I. The main effect of phosgen results from the dissolution of the gas in the mucous membranes deep in the lung, where it is converted by hydrolysis into carbonic acid and the corrosive hydrochloric acid. The latter disrupts the alveolar capillary membranes so that the lung becomes filled with fluid, a state of pulmonary edema. Hydrochloric acid is also partly responsible for the harmful or blistering effects of mustard gas. In the presence of water, such as on the moist surface of the eyes or lungs, mustard gas breaks down, forming hydrochloric acid. Safety. Hydrochloric acid in high concentrations forms acidic mists. Both the mist and the solution have a corrosive effect on human tissue, potentially damaging respiratory organs, eyes, skin, and intestines. Upon mixing hydrochloric acid with common oxidizing chemicals such as bleach or permanganate, the toxic gas chlorine is produced. To minimize the risks while working with hydrochloric acid, appropriate precautions should be taken.